So welcome to electrolysis. In this topic we will look at what happens when we pass electricity through various substances. Some things don't change when we pass electricity through them. For example, copper to a battery, you will notice that the copper gets hot, but it doesn't change into anything else. However, when you pass electricity through a solution of potassium iodide, you see chemical changes occurring. So, what are we going to learn in this topic? So we're going to understand why covalent compounds do not conduct electricity, understand why ionic compounds conduct electricity but only when molten or in aqueous solution. Know that the anion is negative and the cation is positive. Describe the electrode products and the observations made during the electrolysis of molten lead bromide, concentrated and diluted aqueous sodium chloride, dilute sulfuric acid and dilute copper sulfate between two inert electrodes, either platinum or carbon. And finally, construct ionic half equations for the reactions at these electrodes during these particular reactions and classify them as oxidation and reduction. So, before we continue, we need to remind ourselves about why things do or do not conduct electricity. In order for things to conduct electricity, there must be charged particles present, and these charged particles must be free to move. Charged particles will either be electrons or ions, and it's clear you need to be understanding what ones we're talking about. Okay, so you have non-conductors, which we know as insulators. They have no free electrons. Charged particles never conduct whether solid or molten. These are known as covalent compounds. Okay, so covalent molecular compounds like hexane, methane, carbon dioxide do not conduct electricity because they consist of individual molecules. These don't have any charge, and there's no charged particles that can move around. Also, all the electrons are being held in the bonds or next to the covalent or next to the atoms, so they can't move from molecule to molecule. There are a few exceptions, like ammonia and, say, acids, but generally covalent compounds are insulators. Then we have the conductors in which electricity flows. Okay, so metals and graphite, which have free electrons. Ionic compounds, which are molten or dissolved in water, are also conductors because they have free charges that can move around. Okay, so lead bromide would be an example of a conductor when it is molten. There are a few more definitions you also still have to be familiar with in order to understand this topic, like electron current, which is the flow of electrons or ions, an electrolyte, which is a liquid that conducts current, electrical cell, it's kind of similar to physics, like anodes and cathodes, electrolytes, a wire and a battery, and electrolysis itself, which is a way to decompose or break down compounds using electricity. And it involves the formation of new substances when ionic compounds conduct electricity.
Electrolysis is electrical current flow through a liquid which causes chemical changes. Yes, you did hear that correctly. Current flowing through a liquid. Now, not all liquids can conduct. The liquid can be a molten ionic compound or an aqueous solution. In either case, it must be able to carry current. Let's take a common example, table salt. If you heat sodium chloride to over 801 degrees Celsius, it will melt. The liquid will contain free-flowing positive sodium ions and negative chloride ions. This simply means that sodium and chloride ions are free to move within the liquid sodium chloride. Positive ions are called cations. Negative ions are called anions. Now consider putting two electrical conductors into the liquid. Copper would be good as it has a higher melting point. Nothing happens to the ions at this point, but if we connect the two bits of copper to an electrical cell or power supply, then things start to get interesting. We do need to sidestep for a moment to look at electrical current in a metal. From our lesson Behaviour of Metallic Structures, we know that electrons in a metal aren't bound to particular atoms. They form a sea of electrons that can move easily if a potential difference or a voltage is applied across it. This could be from an electrical cell or a battery. The electrons will begin to drift towards the positive terminal of the battery, and this is what happens when current flows. Current is the movement of charge, in this case electrons. Now, let's go back to our molten sodium chloride. We've added our copper wires, let's call them electrodes, and now we'll connect these to an electrical cell. The electrons will start to flow in the wires, and this will cause one electrode to become positively charged and the other negatively charged. This has an immediate knock-on effect in the molten sodium chloride, which you'll remember is a mixture of sodium cations and chloride anions. Anything positively charged in the liquid, in this case the sodium ions, is going to be attracted to the negative electrode. And anything negatively charged, in this case the chloride ions, is going to be attracted to the positive electrode. This is because opposite electrical charges attract. When the ions meet the electrodes, electron exchange happens, and this triggers a chemical reaction. Solids can form, gases can be given off, and new solutions can be left behind. It all depends on the liquid and what material the electrodes are made from. There is more detail about this process in our lesson Interpreting Electrode Equations. There are special names for the electrodes, which are usually metal plates with a larger surface area than a piece of wire. The positive electrode is called the anode, it attracts anions, and the negative electrode is called the cathode, it attracts cations. The liquid is effectively conducting electrical current. The only difference is that the charge carriers in the liquid, in other words the charged particles that are moving, are ions. If a liquid has free moving ions and can conduct like this, it is called an electrolyte. Remember that electrolysis can also take place in ionic solutions as well as molten compounds. The more concentrated that solution, the greater the ion flow rate. Ion flow rate can also be increased by increasing the potential difference or voltage across the cell. We'll be studying several examples of electrolysis in more detail in other lessons. For the time being though, here is a summary of the key ideas about electrolysis. Electrolysis is the flow of electrical current in a conducting solution or molten liquid that causes chemical changes. The conducting liquid is called an electrolyte and has free moving ions. The conducting plates, bars or wires inserted into an electrolyte are called electrodes. Positive ions are called cations and are attracted to the cathode. Negative ions are called anions and are attracted to the anode. When current flows in an electrolyte, it is the ions that move and carry the electrical charge. When current flows in the electrodes and wires, it is the electrons that move and carry the electrical charge.
So what is this electrolysis? Well, electrolysis, as said in the previous slide, is the breakdown of an ionic compound, molten or dissolved in water in aqueous solution using electricity. Okay, so here's an example here. We have an electrolyte solution containing a ionic salt which has been dissolved. Okay, and you can see that an electrode is an electric conductor in contact with the anode. So these would be your two electrodes. The anode is the positive electrode, okay, because it attracts the negative anions, and the cathode is the negative electron, because it attracts the positive cathodes, okay, cations. Okay, and the electrolyte is a substance that forms ions when dissolved. Okay, so cations, as you can see, are positive. Okay, so cat ions are positive and anions are negative. And the way I remember it is put a positive charge in there, okay, put little ears on it. That would be a cat ion, that's positive, and the anions are like onions, okay, and if you eat an onion, then you're going to cry. That's how I remember it anyway. So what happens at the electrodes? Well, here we have an anode and a cathode and completing a circuit in an electrolyte. So the electrolyte contains metal cations, which are positive, as we've seen from the last slide, and non-metal anions, okay, which form when they are dissolved. At the cathode, the metal cations gain electrons and deposit as the metal on the cathode, and we call this reduction. And at the anode, the non-metal anions lose electrons to form the non-metal element at the anode. Now, how do I remember this? Well, I remember it the following way, okay? I go, Leo goes, Ger. Okay, so loss of electrons is oxidation, and gain of electrons is reduction. Okay, Leo goes Ger. So at the anode, the non-metal anions lose. Okay, so we look at that. It's going to be the loss, so it's going to be oxidation. So in terms of a summary of the essential features of electrolysis, 1, ions are attracted to electrodes, be they positive or negative. Negative non-metal ions are attracted to the positive electrode, called the anode. Positive metal ions are attracted to the negative electrode, called the cathode. And at the electrodes, electrons are gained, which we call reduction, okay, or lost, which we call oxidation, by the ions involved. And products are formed at each electrode. So now we're going to look at some examples of electrolysis and some products that form. Okay, so let's look at some true or false questions before we continue on, to see if we really understand the topic so far. Okay, so the best way to do this, of course, is to look at the question and then pause the video and answer it in your own time, come back, see if you got it right. Okay, so electrolysis is the splitting of a substance using electricity. Is that true or is that false? Well, it's going to be true. Electrolysis, electro-cutting. The anode is negative. That would be false. The anode attracts anions, which are negative, but that means it must be positive to do that, because like charges repel, unlike charges attract. Anions are negative. That would be true. Anions kind of similar to onions, which make you cry because they're so negative. Okay, anions are negative. Cathode is negative. Well, the cathode attracts positive charges, so opposite charges attract, so it must be true, shouldn't it? Okay, cathode is indeed negative. And finally, cations are negative. Well, if anions are negative, then cations can't be negative, so it must be false. So how do we predict the products of electrolysis? So ionic bonded salts can only form ions when they are dissolved or melted. Why is this? Okay, so pause the video now and think about that. Okay, so the reason why, of course, is that when it's a solid, all the charges are electrostatically attracting to each other. There's no free charge to move around, but once you dissolve it, then the ions are free to move, and therefore movement of charges is going to be current, electricity. Okay, so they only form ions when they're dissolved because they break up the ionic lattice, or when they're melted because they're energy again breaking up the ionic lattice. But when it's solid, it does not conduct. So you can predict the products of electrolysis by Dr. Harvey's 3 easy steps. The first one is, from the ionic salt's name, determine the metal and the non-metal present. The first part of the name gives the metal ion, and the second part gives the non-metal ion. The metal ion gains electrons to form a metal at the cathode, And the non-metal ion loses electrons to form a non-metal element at the anode. Okay, so you've got to be careful though, because some elements form diatomic molecules, and also iod goes to iron. So chloride goes to chlorine. Okay, and that's also another example of a diatomic element. These three easy steps only happen especially when they're melted. Okay, there might be some examples which we'll look at later where there might be some exceptions to my rules if they are dissolved. So let's have a look at this particular question here. Using Dr. Harvey's three easy steps, can you work out what forms at the anode and what forms at the cathode? Okay, so again, pausing the video, see if you can actually write the table in your book and try and actually answer it for yourself before pressing play, and we'll go through it together. Right, so welcome back. So the first one is sodium bromide. Okay, so we're going to work out what forms at the anode and forms at the cathode. Okay, so at the anode, it's going to attract the negative ions. So which one of those is going to be the negative ion? It's going to be the bromide. Okay, so what's going to happen is the bromide is going to be turned into bromine. Now be careful, it's bromine, not bromide, because bromide's the ion and bromine is the molecule that's made from the ion. And the cathode, therefore, is going to form sodium. Potassium iodide is going to form iodine. Okay, again, notice it's iodine, not iodide. And good old potassium, which we eat our bananas for. Okay, calcium fluoride is going to be fluorine, that wonderfully toxic gas, a highly reactive gas, and calcium is the metal at the cathode. And magnesium oxide going to be oxygen, and magnesium. And finally, lithium chloride, chlorine, and lithium. So hopefully you got 100% for that. Okay, if not, go back to the notes and analyze where you can improve.
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using 2 carbon electrodes, an ammeter, and a power supply. The white powder is lead bromide. Switch on the power supply, and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now, and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be? The gas is bromine. nothing obvious appears to be happening at the left-hand electrode, pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid? Change the compound from lead bromide to zinc chloride and the products of electrolysis will be different. What would you expect to see happening when electricity is passed through molten zinc chloride? This time, bubbles of a very pale gas appear at the positive electrode. It turns damp blue litmus paper red and bleaches it lighter. So what gas is it likely to be? Again, nothing appears to be happening at the negative electrode on the left. But pouring off the molten zinc chloride reveals a bead of pure zinc. In industry, electrolysis is carried out on a huge scale. Massive amounts of electricity are used to extract reactive metals, like aluminium, from their ore.
Okay, so the first example we're going to look at as electrolysis is the example of molten electrolysis. We're melting the salt. Okay. So basically, if you put the electrodes into solid lead bromide, flick the switch, you're going to see nothing happen. Okay, because it has to be melted. But when the molten lead bromide is melted, you'll see that electrons start to flow through the circuit. There is bubbling around the electrodes, especially the anode, connected to the positive terminal, and a brown gas is coming off, and then nothing seems to happen at the cathode connected to the negative terminal, however. However, once you pull it out, you'll see that a metallic shiny metal is on its surface. Okay. And when you stop heating it, the lead bromide solidifies and the circuit again closes down. So what's happening? Okay, so what's happening with lead bromide is that you're making lead 2 plus and bromide ions by melting it. So at the cathode, the lead 2 plus is gaining electrons to become lead. Okay, so it's being reduced. And at the anode, the bromide is losing electrons to become bromine. Okay, it's being oxidized. So this explains why you see it. You see brown bromine gas forming at the anode and lead forming at the cathode. And that's the full equation there in terms of what's happening. And this is what it actually looks like if you're doing the electrolysis. Okay, the positive lead ions are attracted to the negative electrode, and then they're gaining electrons to become lead metal. And then the negative bromide ions are attracted to the positive electrons. They're losing the electrons to become bromine. Okay, forming that bromine single bond. Just reinforcing that, at the negative electrode, which is the cathode, the lead ions are attracted to the negative electrode. The lead 2 plus ions gain 2 electrons, and the ionic half equation is thus, okay, which we've looked at in the previous slide. You're making lead by getting electrons, and at the anion, the bromide ions are attracted to the positive electron, okay, and positive electrode, and the bromide ions lose the electrons to form bromine atoms. Okay, and you see that as diatomic bromine gas, Br2. And the half equation, as we've looked at before, is the 2 bromide are then losing electrons and forming bromine. Okay, so this is all about the redox reduction oxidation. So therefore, the products of this reaction are going to be lead metal at the cathode, the shiny liquid, usually at the bottom of the reaction vessel because lead's quite dense. Okay, it kind of falls off, goes down, and bromine appears as bubbles of brown gas at the positive electrode or anode. And the overall reaction is lead 2 plus 2 bromide minus, giving lead and bromine. So another example of electrolysis is, with a special case here, this is an interesting case due to the acidic nature of it, is the electrolysis of dilute hydrochloric acid. Okay, so the last one was a solid melt. What we're doing now is we're adding the compound we want to electrolyze to a solution of water. Okay, so at the negative electrode, what is happening is that hydrogen ions are attracted to the negative electrode. Okay, so it's H plus from the acid, okay, and the H plus ions, the protons, gain an electron each. And the hydrogen ions form a covalent bond and create bubbles of hydrogen gas. Okay, and the ionic half equation for this is 2 protons plus 2 electrons giving hydrogen. Okay, so the protons have been reduced to hydrogen. At the positive electrode, the chloride ions are attracted to the positive electrode. Chloride ions lose their extra electrons. They have been reduced to form chlorine atoms. These chlorine atoms then form diatomic chlorine gas with a nice green color. Okay, and the half equation is thus. Okay, 2 chloride losing 2 electrons to become chlorine. It's been reduced. Therefore, the products will be hydrogen gas forming bubbles of colorless gas at the negative electrode, the cathode, and a green gas forming, which is the chlorine, at the positive anode. And that's the full equation, 2 protons plus 2 chloride ions giving hydrogen gas and chlorine gas.
Sodium chloride is one of the world's cheapest and most widely available raw materials. It's found as rock salt in vast deposits underground, and it's dissolved in all the oceans of the world. The electrolysis of sodium chloride solution is an important industrial process. Mix the salt with water, pass an electric current through it, and a variety of useful substances are produced. To work out what's going on, here's a much simpler setup in the lab. 2 electrodes immersed in sodium chloride solution are connected to a power supply. The electrodes are made of carbon. They're supported by an insulated hook. See what happens when an electric current is passed through the solution. What evidence is there that chemical reactions are taking place? Bubbles appear around both electrodes, a sign that gases are being produced. To collect the gases, a test tube full of sodium chloride solution is placed over each electrode. Gas displaces the solution and collects in the top of the tube. So, what are the gases? Both are either very pale or colourless, but they can be identified by simple tests. The gas collecting at the positive electrode is tested with damp blue litmus paper. It goes red and quickly bleaches white. The gas is chlorine. The gas collecting at the negative is tested with a lit splint. It pops, a sure sign that this gas is hydrogen. So, why does the electrolysis of sodium chloride solution produce hydrogen and chlorine? Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen compete to gain electrons. The hydrogen ions win out. They lose their positive charge and form bubbles of hydrogen gas. Competition also happens at the positive electrode. This time, chloride ions win out, losing their negative charge and forming bubbles of chlorine gas. Industrially, the electrolysis of sodium chloride solution can provide us with many useful materials. Chlorine is used as a disinfectant in swimming pools. Hydrogen is used as rocket fuel. And the sodium hydroxide solution left behind is used in the manufacture of bleach.
So the next example we're going to look at is what happens when you electrolyze a solution of brine. Now, brine is a concentrated solution of sodium chloride. Another important aspect is what happens when you look at sodium chloride solution. Okay, and we can compare that when we do it when we melt sodium chloride and the differences that we might observe. Okay, so if we had solid sodium chloride and we melted it, okay, we would undergo electrolysis. And again, why are we melting and dissolving? Because we want to make those ions free. Okay, sodium chloride salt is not free to move. It's stuck in its crystal lattice. Okay, and if you can't move, you can't form a circuit, you can't undergo electrolysis. So the half equations, at least for solid, are going to be 2 sodium ions plus 2 electrons giving 2 sodium. Okay, so you'd see metal at the cathode, at least when you're melting it. Okay, and you'll see chlorine gas forming at the anode, which makes sense. Okay, you're basically just splitting sodium chloride into sodium ions and chloride ions. But with a concentrated sodium chloride solution, you've now got water in the equation. Okay, so you're dissolving the salt now in water. You'll actually end up forming hydrogen gas, because what's happening is that the water is actually being split to form hydrogen gas at the cathode. Okay, so instead of getting sodium metal, you'll get hydrogen gas at the cathode. Okay, so this is actually slightly more complicated than the simple melt example. So what's actually happening? Okay, so because we're dealing with sodium chloride, okay, you'll have sodium ions in solution. Fair enough. However, water, because we're now doing in solution, can also form ions. Okay, ever wondered why the pH of water was 7? Well, now you don't have to wonder anymore. Okay, so water actually forms ions in solution. So it's an equal mix of protons and hydroxides. So a small amount of water molecules actually do this, about 1 times 10 to the negative 7 moles per litre is the concentration, roughly. So quite a small amount. However, it means that there is actually protons in solution. So the sodium ions and the hydrogen ions from the water compete at the cathode. The sodium ion is very reactive, which we would have learnt in reactivity last year, so it does not last long enough to actually get to the cathode and form sodium metal. Another way of looking at it could be that water gains electrons to form hydrogen atoms when they combine to form colorless molecules of hydrogen gas. Okay, so you could look at it like this. 2 water molecules come along. They gain 2 electrons, okay, and form hydrogen gas, and it's a gas plus 2 hydroxide aqueous and the liquid water. Okay, that's another way of possibly approaching it. Okay, you can then see more easily why a solution of sodium chloride actually comes very alkaline, because you're producing a large number of hydroxides. Okay, now you'd also note, well, hey, wait a minute, there's hydroxide ions also present now. So why don't the hydroxide ions get attracted to the anode and do something? Okay, so both the chloride ions and the hydroxide ions are attracted to the positive anode, but it's slightly easier to remove electrons or oxidize the hydroxide ion than the chloride ion. But there's not much difference. The real difference comes from the fact that you've got a larger number of chloride ions in solution, because we're using brine here. It's saturated chloride, sodium chloride solution. Okay, so basically it's a competition, and because there is more chloride ions about, the chlorides win. So the chloride ions lose electrons, they get oxidized, they form chlorine atoms, and then these chlorine atoms form the green diatomic chlorine gas, which you see at the anode. And that's the half equation there, if we're using the water example of gaining electrons. Okay, so 2 water plus 2 chloride ions give hydrogen gas plus chlorine plus 2 hydroxide ions. So the next example we'll look at is looking at copper sulfate solution. Okay, so in copper sulfate solution, at the negative electrode, copper ions are attracted to the negative electrode. The copper ions gain 2 electrons each, and the copper ions form a copper metal on the electrode. Okay, you see it as copper. And the half equation would be copper 2 plus gains 2 electrons, oxidized into copper. So what's happening? Well, just like in the previous example, water is in equilibrium. Okay, so it's going to form protons and hydroxides. Okay, and the sulfate ions and hydroxide ions are attracted to the positive electrode. Okay, so you've got these 2 different negatively charged ions in solution. The sulfate, however, is harder to oxidize, so the hydroxide ion formed from the water is oxidized instead. And the hydroxide ions lose their extra electrons to form oxygen atoms. And the oxygen atoms join up in pairs to form diatomic oxygen gas, O2. And the ionic half equation for this is given as 4 hydroxide gives 2 water plus oxygen and 4 electrons. There is another way to look at it, of course. You could say, well, you've got 2 water, which is a liquid, of course, going to oxygen gas plus 4 protons plus 4 electrons. It's still losing electrons, okay, so still being oxidized, but in this particular case we have these 4 protons forming, which in a way explains more easily why the solution becomes more acidic. Okay? And due to this acidity, the copper ions and the hydroxide ions you get rid of because they're being reduced as products and oxidized as product of the electrodes. And the hydrogen ions from the water aren't being actually used up. And neither are the sulfate ions. Okay, so now you've got sulfuric acid in there. Okay, solution becomes essentially dilute sulfuric acid. So the products are going to be copper metal at the negative electrode, oxygen as a colorless gas at the anode, and that is the overall equation. 2 copper 2 plus 4 hydroxide gives 2 water plus 2 copper plus oxygen. And as I've just said, eventually all the copper ions are used up to make copper. All the hydroxide ions are used up to make oxygen. So it only leaves protons and sulfate ions in solution, which creates sulfuric acid, which can then undergo further electrolysis, which is the last example. Okay, so the only positive ions here are going to be the protons. So the protons each gain an electron. The hydrogen ions then form a covalent bond to form bubbles of hydrogen gas at the cathode, and the half equation is thus. Okay, 2 protons plus 2 electrons giving hydrogen. Now at the positive electrode, you have again water losing protons to form hydroxide ions. Okay. Because again the sulfite ions are too difficult to oxidize, so you get this slitting of the water to form protons and hydroxides. Okay, which I mentioned in the last example. The hydroxide ions lose their extra electrons to form oxygen atoms, and the oxygen atoms join up in pairs to form diatomic oxygen gas. And the ionic half equation for this is thus. 4 hydroxide going to 2 water plus oxygen plus 4 electrons. The products of electrolysis with dilute sulfuric acid are going to be hydrogen gas, forming as bubbles at the cathode, and colorless oxygen gas forming at the anode. In a 2-to-1 ratio, you're going to end up with more hydrogen forming than oxygen in that particular example. Okay, which you can see here because of the ratio here. You've got 2 hydrogen to 1 oxygen, so more hydrogen gas is going to be formed. So just to give a couple of a couple of examples of revision, match up the words with their descriptions. So pausing the video now and seeing if you get the correct answers. This is also going back onto your kind of remove and shell stuff as well. Okay, so what's the test for oxygen? So the test for oxygen, labeling that 1, is going to be relights a glowing splint. Test for hydrogen, so 2, is going to be make a pop test. They're all popping when lit. An electrolyte is going to be a substance that can be broken down. The anode is going to be the positive electrode because it attracts the anions. The cathode will therefore be the negative electrode, if I can find it. There it is. The anion is going to be a negative ion. The cation is going to be a positive ion, and electrolysis is going to be splitting up a substance using electricity. So hopefully you got 100% for that. And there's an example of an activity we're going to do in class.